Nice. So today we are going to start a new topic here. So welcome back and good morning to you all. Today we are going to talk about state space modeling and analysis. And this is different from what we have done so far. Okay. So this is quite different from what we have done so far. And you will see why. So if you recall our transfer function modeling, you would remember that in transfer function modeling, we actually had quite a few assumptions, right? While doing transfer function modeling, we assumed quite a few things about the system, right? That we were modeling using transfer functions. Right? Again, first of all, what is a mathematical model of a system? A mathematical model of a system is a mathematical description that somehow gives you a relationship between inputs and outputs for that particular system. So for any system, in order for to qualify as a system, it should have qualifying inputs and qualifying outputs, and the system should interact with qualifying inputs and produce qualified outputs. And the interaction between and the relationship between those inputs and outputs are given by the mathematical model of the system. Okay, so that is how really things work in the mathematical modeling space. And one of the mathematical modeling techniques that we employed was transfer function modeling, right? And we saw that transfer function modeling was an easy task as long as you understand Laplace transform, inverse Laplace transform. But on top of that, in transfer function modeling, you had quite a few assumptions, right? So let's write those down first. Okay. Let's recall what assumptions we made while actually doing transfer function modeling. Okay. So I would say these are the assumptions of transfer function modeling. So of course I would by now I can assume TF means transfer function, right? Without actually telling you. Yes, someone is asking, won't we be doing Bode plot and Nyquist theorem? No, we shall be doing Bode plot and Nyquist theorem after we complete state space analysis. Okay, we shall go back to transfer functions. Okay. I already gave you the precursor of Bode plots in signals and systems. You already know how to figure out things about similar graph papers, how to draw things on similar graph papers. You already know about those. And in that discussion, in the frequency response discussion, so what you are referring to Bode plot by saying Bode plot and Nyquist plot, those are called frequency response, and I shall deal with frequency response in the end. Okay, after we complete state space modeling. Okay. Anyway, assumptions behind transfer function modeling. The first assumption is that the system has to be linear and time invariant. Okay. The system has to be linear and time invariant. So LTI systems. So that is the first assumption. Okay. Again, for our assumption, we assumed continuous time systems. But again, if you don't have a continuous time system, instead, if you have a discrete time system, in that case, you can have transfer functions, but only difference would be the transform that you apply, the integral transform that you apply won't be Laplace transform, but instead it would be Z transform. Right? So you won't have a transfer function in terms of C, but in terms of Z instead. So I'm not writing continuous time. But then again, next condition is that the system will have to have zero initial conditions. So for all transfer function modeling, these two conditions are essential. if any of these, rather three conditions really: linear, time invariance, linearity, time invariance, and having zero initial conditions. If any of these conditions are violated by a system, you cannot model it using a transfer function, using transfer function technique. And this is not really a rule. For the sake of simplicity, the system should be single input, single output. Again, this is not a condition really, but for the sake of simplicity, the system should be CISO. So this is an essential condition. This is also an essential condition. Okay, this is not really an essential condition, but again, you probably have seen that if you have multiple input, multiple output system, I mean, you don't even have a single transfer function. You would have multiple transfer functions. Okay, relating every single input with every single output. Say for example, if you have a system which takes 3 inputs and produces 2 outputs, so that system is a MIMO system, multiple input multiple output system. For that system, you don't have a single transfer function. Instead, you have transfer functions that that relate every single input with every single output. So I have 3 inputs and 2 outputs. So that system will be described by 6 different transfer functions. So essentially we would have a transfer function matrix for that. Okay, really complicated to understand, I think. Okay, so ideally, for the sake of simplicity, the system should be single input, single output, but nonetheless these conditions must be satisfied. These two must be satisfied. Okay, and this is another one that I'm writing here because the modeling technique becomes very complicated the moment we don't have a CISO system. Okay, so that's the underlying, those are the underlying conditions when we do transfer function modeling. Now on top of that, we have to understand that in the transfer function modeling technique, we already are losing a little bit of information about the system. Okay, say I have a linear time invariant system. Okay, so say the first condition is satisfied. If somehow the second condition is not satisfied, in that case, what happens? I cannot construct a transfer function model. But then there is another problem. What problem? I mean, if I construct the transfer function model of a system, I also don't get to see how the system behaves if the system has non-zero initial conditions. Imagine a simple electrical circuit. Okay, if I am doing transfer function modeling, then I won't be able to see how the circuit behaves if a capacitor is storing some initial charge and inductor is storing some initial magnetic field. If something like that happens, then I do not have any reliable way of using transfer functions to figure the response out, right? So I have a system where there are non-zero conditions, non-zero initial conditions, and I have a transfer function of the system. Then I do not really have a way of figuring out the response of the system to those non-zero initial conditions, because while developing the transfer function model, we completely discarded any initial conditions really. So if there are any initial conditions, we cannot reliably figure the responses out into those. So that is something you have to remember. Okay, so these are the conditions. Now of course, in reality, everything is non-linear. Nothing is linear really, right? There is not even a single thing that's linear, right? Even if you say that, okay, I have a simple resistor that resists the flow of current and the voltage to the resistor is proportional to the current and the proportionality constant is the resistance, then this is, I would say, this is just a simplification. This is just a simplification. What happens when you for example, create a voltage gradient on a conductor? Okay, when you create a voltage gradient on a conductor, what happens? The free electrons in the conductor actually gets a certain push, so they get a certain force, I would say. Okay, and then they try to move in a certain direction uniformly. Okay, and those electrons actually bump into each other and the atoms of the crystal itself, right? So atoms of the crystal itself, right? This is not just the lump model. Okay, this is not just the matter of the lump model. This is also a matter of fact that, for example, the way we assume is that the electrons start moving when we apply a voltage in a conductor. Okay, and they bump into the crystalline structure of the molecules of the conductor, and that actually results into some wastage of their energy, right? Some wastage of their energy. Okay, and that manifests as the resistance of the conductor. Okay, just like that. But this is not really true. What happens is, the moment the electrons start flowing in a conductor, what happens is that they bump into the crystalline structure, right? The moment they bump into the crystalline structure, okay, the molecules of the conductor, what happens, those molecules start vibrating, right? And the moment they start vibrate, okay, they behave as small dynamic systems themselves. Okay, they behave as small dynamic systems themselves. Okay, and as such, there is nothing really linear here, right? So you can make it behave very weirdly, right? So if this current is a alternating current, for example, if you increase the frequency, you will see the resistance is increasing. What? This is called skin effect somehow. Okay, so you might have studied this in power systems engineering, right? So if you provide high enough frequency, what happens, the electrons tend to move towards the outer shell of the conductor. Okay, and nothing really flows to the inner core of the conductor. There are so many things that happen in a simple conductor. Okay, and this is really not the Ohm's law. Okay, this is not really the Ohm's law. Okay, and the Ohm's law really should be defined only at a point, and at a point we can only say, for a conductor that is an ohmic conductor, okay, we can say at a point, this is Ohm's law. Okay, the current density at a given point is proportional to the electric field intensity. So that is only something we can say. So this is valid for a single point. Okay, so kind of Ohm's law is valid for only for a single point in a valid ohmic conductor. There are so many non-ohmic conductors, right? Okay, any conductor that conducts through vacuum discharge or things like that, maybe a fluorescent lamp, anything like that, okay, that's a non-ohmic conductor. Any semiconductor device is a non-ohmic conductor. Okay, Ohm's law do not apply. So really, in life, nothing is linear, right? And nothing is linear, right? And as such, we cannot really assume linearity everywhere. So what we instead do, we assume that the system is linear, or that the devices or equipments or the elements that we are using are linear about the operating point. So if I have a resistor that is carrying 1 ampere current, I would assume that 1 ampere current, and in the frequency range, whatever frequency range I'm applying, in those ranges the element behaves linearly. We assume things like that. Okay, so linearity is nothing but an assumption in real life. Okay, linearity is nothing but an assumption. Keep that in mind. Every single thing is non-linear if you just dive deeper. Okay, every single thing is non-linear. Nothing is really linear. It's just an assumption, and sometimes this assumption is a good assumption. Okay, sometimes we can make judicial assumptions, say this is linear. On the other hand, time invariance is more or less fine. Okay, is not that bad assumption as linearity. Okay, so we often see many time invariant system. If you create an electrical circuit, it would probably be a time invariant system, right? Yeah, seeing at least like that. Okay, if you create a small mechanical system, it is probably going to be a time invariant system. So that is a kind of a good assumption. But again, in real life, there are so many systems that are time variant, right? Time variant. Okay, for example, I am teaching you right now. This entire process is a time variant system. Okay, this entire teaching process is a time variant system, because if I give you the same input, but say for example 2 months later, okay, after the end of this semester, maybe none of you will attend the classes, right? So why? Because applying the same input at a different time won't produce the same result, right? In this system, at least. So this is a time variant system, and in fact many systems in real life are time variant. Okay, but again there are many time invariant systems which for which we do not have to assume time invariance, but those systems are time invariant for the most part. Okay, and the worst assumption here is the zero initial condition. The moment we are assuming zero initial conditions, we are kind of throwing away some inherent behaviors of the system, right? So if you are having capacitors, inductors and everything, so if you are doing transfer function modeling, you are going to assume that before you start the system, everything is completely discharged and demagnetized. Okay, if you have a mechanical system, you are going to assume the springs are completely relaxed, the dampers are not moving, everything is completely relaxed, nothing is storing any energy. Okay, so that zero initial condition assumption is also kind of a bad assumption. It pretty much removes many uh, um, insights about a certain system, right? And in fact, you will see what I'm saying, what I am talking about. Okay, keep that in mind. So in reality, systems are mostly non-linear. Okay, we only assume linearity about the operating point. Okay, many systems are time invariant. Also, many systems are time variant, and for the most part, we hardly ever find systems that carry zero initial conditions. Most systems do carry non-zero initial conditions, right? Non-zero initial conditions. All right, just like that. So, and also, for the sake of simplicity, we assume single input, single output systems while modeling transfer function. Okay, while modeling with transfer functions, and I will give you a proper example later that will showcase these things, all these things. Okay, all right. So now here comes Radloff Emil Kalman. Okay, so Kalman. So this he was a Danish scientist, I think. Okay, and he is called the father of modern control engineering. Okay, father of modern control engineering, and he pretty much revolutionized the way we think about systems, how the way we think about designing control systems, right? So he is most developed, rather the most of the developments he did was in 1950s and 1960s. So I told you in the very beginning we started our discussion with things that were developed in 1940s. Okay, now we have just jumped to 1950s and 1960s. Okay, so R.E. Kalman. So Kalman actually developed quite a few things. One of those things is the state space modeling technique. Okay, so Kalman developed the state space modeling technique. And to be very honest, whatever you have learned so far, in my opinion, is just there for you to understand the things better. Okay, so if I ask you what is the utility of Routh-Hurwitz modeling, okay, Routh-Hurwitz table, uh, in today's paradigm, right? We are living in 2020. We do have computers, right? What is the point of Routh-Hurwitz? Really, if you think about it, okay, it is just to have a proper insight about the system. If you study Routh-Hurwitz, you would understand by looking at a polynomial, you'll be able to see, okay, it is violating the necessary conditions, so this must be unstable. Just giving you better insight. But truly speaking, what is the utility of Routh-Hurwitz today? If you think about it, really nothing. There is no utility of Routh-Hurwitz in today's perspective, right? In living in 2020, I mean, what is the point of Routh-Hurwitz, right? We can just put it on a computer and it will give me the exact locations of the roots, right? I do not need Routh-Hurwitz. Okay, you studied root locus technique. Of course, that was a fantastic technique, and this is quite wonderful. Without actually solving anything, really, we are finding out the roots of the closed loop poles, locations of the closed loop poles for varying gain in the forward path, right? We're actually solving for the roots without actually solving for the roots. That was a fantastic technique. But if you ask a computer program today, will it apply any rule of the root locus? No. It will just vary the gain and calculate the roots and plot it on your screen. Just like that. So is there any reason really to study root locus technique today? Yes, you would get better insights about the system. Your understanding of systems will be much better. Okay, but is there any usefulness of that today? Answer is no. The same thing goes with everything else in classical control. So whatever we have studied so far is classical control. The same thing goes with Nyquist plot. The same thing unfortunately does not go with Bode plot. The Bode plot is the only thing. Again, you will understand this as time goes on, and if you ever do design control systems. The Bode plot is the only thing from the classical control paradigm that has survived the test of time, and that is actually still used today. Okay, that frequency response thing. Okay, Nyquist plot is also a frequency response thing, but that is not really used for anything else, much of anything today. But state space modeling is known as modern control. Okay, and this modern control technique, so this state space actually called the state space modeling is called modern control. Okay, and here whatever we learn here actually used nowadays. So if you are a control system engineer, okay, you are designing control systems, you are probably not using transfer function approach. Okay, and if you are using transfer function approach, you are probably using only Bode plot as the classical tool that you have. Okay, if you are designing some controller using the classical techniques, you are probably using Bode plot for that. Okay, and the other techniques are not really useful nowadays, right? Because those techniques were developed back in the day, back in 1940s, and before that even. Okay, because people didn't have computers, people didn't have calculators, so scientists and engineers, they tried to develop techniques that could ease the lives of engineers, right? So without actually calculating anything, we would know everything. That was pretty much the purpose back then. Okay, but nowadays we can, since we can calculate everything, those things are pretty much obsolete for the most part. So state space modeling is also known as, so it's also known as modern control. So Kalman tried to lift these assumptions. Okay, so before that, everyone did control system engineering using transfer function techniques, right? So Kalman did try to alleviate these assumptions, and he really was successful. So he is pretty much called the father of modern control engineering because of that. Okay, Kalman is, I'd say, was a legend. He died only I think in 2016. I think so. He died only a few years ago. Okay. So what is the state space model? Okay. Again, we are going to study a fair bit of state space modeling in this course. I think I shall take 4 classes on state space modeling in total, 4 or maybe 5. I don't know. Maybe 4 probably. Okay, all right. So in state space modeling, what we do, we remove these assumptions. We remove the assumption of linearity, remove the assumption of time invariance, remove the assumption of zero initial conditions. Okay, and we also remove the simplicity assumption that the system would be C. So all these assumptions are removed. So if I have a nonlinear system, you want to mathematically model it, what technique would you choose? State space. If you have a time variant system, what technique would you choose? State space. If you have a system where you want to see non-zero initial conditions, what technique would you use? State space. If you have a multiple input, multiple output system, what technique would you use? What modeling technique would you use? Again, state space, right? And if you have every single one of these combined with one another, okay? If you have a non-linear time variant system, what technique would you use? State space. Okay? You get the idea, right? The idea is that state space modeling can be done for any system, really, any system. If you understand the mathematics, if you understand the relationship between the input and the output for that system, you can do state space modeling for that system. So state space modeling can be done for any system. Okay, as long as you understand the mathematics. If you don't understand the mathematics, how can you even model it, right? So just keep that in mind. So this method, rather, let me be very clear. When I was taught by one of the legendary teachers in JU. So actually, when I studied these, so it felt like, why are we studying this? Because we already know about transfer functions. We already have studied that by heart, kind of. Okay, so why do we need state space technique? And this state space technique would seem like oddball for us in the very beginning, but later on, as we went on, it felt like this is the only thing that I really needed to learn. Okay, and as such, you will see that too. Okay, probably, I hope so. Okay, so these are the assumptions. So state space technique, So let me just write it down here. State space modeling works on nonlinear systems. Of course, if it works on nonlinear system, it is also going to work for linear systems, right? If I develop a mathematical model that works on nonlinear systems, it will also work for linear systems, obvious. Okay, nonlinear systems, time variant systems. Okay, nonlinear systems, time variant systems, systems with non-zero initial conditions, MIMO systems, pretty much every system. So state space modeling works on pretty much every system. Okay, if you want to model a digital system, a computer system, okay, using state space modeling, you can. Pretty much it works on every system. Now the way you do the state space modeling for different kinds of system would be different. The way you would handle different types of nonlinearity would be different. The way you would handle different types of time variance would be different. The way you handle non-zero initial conditions is built in to the state space model. Okay, so this is pretty much built in. Okay, in state space modeling you don't have to assume this is pretty much built in always. Okay, and also this is built in. Developing state space modeling for new system, this is built in. But how you track nonlinear systems and how you actually model for nonlinear systems, how you model for time variant systems, okay, for that you have to do certain techniques, certain things in it. Unfortunately, we are not going to learn that. So we are going to use state space modeling exclusively for the purpose of dealing with non-zero initial conditions, okay, and MIMO systems. We shall be using state space modeling technique to deal with MIMO systems and non-zero initial condition systems. Okay, systems that do not have zero initial condition. Especially for these purpose, we are going to use this. We are not going to use this state space modeling technique for modeling nonlinear systems, because this is a course on linear systems only. So we are not jumping on that. Okay, and forget about time variant systems, because that is something taught to master's degree students only. Okay, I don't think anywhere in the world, I mean, undergraduate control system course would involve time variant systems. Okay, so forget that completely. Okay, so again, I told you, just keep that in mind. Okay, no, you can very easily do nonlinear system modeling and time variant system modeling using state space. But here we are going to employ state space modeling for for modeling non-zero initial conditions and modeling MIMO systems. But you have to understand that a modeling technique that is capable of modeling nonlinear systems is also capable of modeling linear systems, obviously. A modeling technique that is capable of modeling time variant systems should also be able is also capable of modeling time invariant systems, obviously. A technique which is capable of modeling non-zero initial conditions will also be capable of modeling zero initial conditions. Again, a system which is capable of modeling MIMO systems will also be capable of modeling CISO systems, because these are just the supersets, right? Right? So just like that. I think you understand my point here. Okay, so this is the point. State space modeling works on pretty much every system, right? Doesn't matter whether it's a linear system, non-linear system, does not matter. Okay, okay. I would say state space modeling even works on. Okay, that makes the language pretty clear here, right? So now, for our purpose, we are going to assume linear systems, and we are going to assume time variant systems, time invariant systems. Okay, but we are not going to assume the other two conditions. Okay, so that have, so we're going to assume linearity and time invariance that have non-zero initial conditions. Also, we shall not rule out the possibility of dealing with MIMO systems. So we would see a few examples of MIMO systems, but we won't be dealing with MIMO systems regularly. Okay, that keep in mind. So let's we should keep our expectations straight here. Okay, so that is the part of the thing. So we are assuming linearity and time invariance just as usual. Okay, so now let's start with the very basic here, very fundamental understanding here. Okay, so now how did we start developing the transfer function model of a system? How did we start developing the transfer function model of a system? If you recall, we actually started with the differential equation, right? We actually started with the differential equation, and that is a good point to start, because when we started with the differential equation model of a system, there wasn't really any condition behind it, right? If you have a dynamic system and if you understand the mathematics, you can always write the differential equation or differential equations representing the system, right? Now on top of that we imposed conditions, but the differential equation itself did not come with any condition, right? We imposed conditions of linearity, we imposed condition of time invariance, we imposed conditions of the zero initial conditions on the differential equation, on top of the differential equation. Okay, then we applied Laplace transform. Okay, so in order for the applicability of transfer function modeling, we assume these things on top of the differential equation. Now let's say I have a third order system. Let's say I have a third order system that has a differential equation that kind of looks like this. Say I have a third order system, okay, that looks like this. So the differential equation of the third order system looks like this. Let's say and the system here, I'm not going to draw the transfer function model, but you can understand what I'm going with this. So this is a system, okay, this has an input and an output. So input and output, input is represented with x here, output is represented with y. Again, these are the generic terms that we use for representing input and output. Okay, I'm no longer saying reference and control variable, because those nomenclatures really are there for transfer function models mostly. Okay, and this is way deeper than that, really. Okay, so you're using generic names for inputs and outputs. So this is the input and this is the output, and this is the system. We can do the transfer function modeling. So I can say this is xs, this is ys, and this will have a transfer function gs in that case, and ys would be the product of xs and gs. But we are not going to do that here. Okay, we are going to do that to just tally our result. Let's say the relationship between the input and the output here in this one kind of looks like this: a3 d3y dt3. So again, everything is dependent, derivatives are with respect to time, of course. Say a2 d2y dt2 plus a1 dy dt plus a0 y equal to say b0 x. Okay, I'm not writing t, you have to understand this is yt, this is xt, understandably. So this is the relationship. There is something I just want you to notice. Okay, there is something I want you to notice, is that right at the very beginning I can divide everything by a3. I can divide everything by a3, right? I can divide everything by a3. So I can write this as a2 by a3. This becomes a1 by a3. This becomes this becomes a0 by a3. This becomes b0 by a3. Okay, so in the mathematical, in the differential equation itself, I can divide everything by a3. Okay, and as such, this is just a constant, right? Now here is the point. We assume a1, a2, a3, a0, b0, all these to be constants. Okay, and only if these are constants, then this becomes a linear time invariant differential equation. So we are assuming LTI system here. LTI assumption is there. Okay, and that is why we are assuming that a0, a1, a2, a3 and b0 for this particular example. This is an example. Okay, example. We are assuming these to be constants. These are constants. Okay, again, any moment you have any difficulty understanding any of these, right? So really speaking, this is just a constant. Instead of writing that, I'm just calling this a2 simply. I could call this anything else, a1, just a0, just b0. My point being, if I give you a differential equation that looks like this, you can always divide with the coefficient of the highest degree polynomial, highest degree derivative here, highest order derivative here, and you get a polynomial differential equation like this. Okay, so this is kind of a small thing that I need to make clear first. Okay, I am writing, so essentially I did not write a3 here. Okay, I assume that to be 1, but instead I can say I can actually divide everything by a3 and whatever values I get will be there, just like that. So imagine, again, this is kind of a very simplified example. Okay, but I am starting with a simplified example because things would be pretty clear as we proceed. Okay, again, again, if we now want to develop the transfer function model, what are we going to do? If we want to develop the transfer function model, now we shall assume. Yes, someone is asking, why did I divide with a3? Will that turn into an advantage? Actually, yes, it is going to turn into an advantage here. Okay, rather just a very small, minute advantage. Okay, but it will be there nonetheless. You know what? Let me just write a3 here. Doesn't really matter. Okay, you will see where the advantage actually went. Okay, I shall let you see it anyway. Okay, but keep in mind, in reality we always try to divide with the coefficient of the highest power. Just keep that in mind always. Okay, all right, so now we already have assumed linearity and time invariance. That assumption will be there. Okay, now if I want to develop the transfer function model, now would be the time to assume zero initial condition. So we shall assume, so we have already assumed linearity and time invariance by making sure that these are constants. Okay, and assume zero initial conditions, and so zero initial conditions, and if I assume zero initial conditions and then apply Laplace transform, so then it will become a3 s cube ys plus a2 s square ys plus a1 s ys plus a0 ys plus b0 xs, sorry, equal to b0 xs. Okay, where I am assuming the Laplace transform of xt is xs, so of course these are xt, huh? These are yt, these are all functions of time. Okay, okay, so I'm assuming that the Laplace transform of xt is xs and yt is ys, and of course if you combine them, and you will get the transfer function, which is defined as the ratio of the Laplace transform of the output to that of the input under zero initial conditions, which we already assumed. Okay, that's gonna be b0 by a3 ss cube plus a2 s square plus a1 s plus a0, something like that. But today we are not going to do that. This is something we are not going to do. So this is the transfer function. Of course, I believe all of you already know that, right? This time around we are not going to do that. Instead, this is our differential equation. We shall treat it differently. Okay, so this is our differential equation. Okay, d cube, let me just write it down, copy it down here. This is our differential equation. Okay, Now, time for introducing certain notation. I am writing this as a3y triple dot plus a2y double dot plus a1y dot plus a0y equal to v0x. Okay, so these dots on top would mean derivatives with respect to time. Okay, so we actually have two different types of variables here, time variables and space variables. And when you differentiate with respect to a space variable, say for example, say we define some, say for example, we are differentiating with respect to x, y, z, things like that, we write a dash. Okay, and when you differentiate with respect to time variable, we put a dot. Again, this notation is actually heavily used in partial differential equations. Dot means a derivative with respect to time, and dash means a derivative with respect to x, y, z, things like that. Okay, space variables. Okay, and if I differentiate with respect to time variable, we put a dot. Okay, if I do a second derivative with respect to a time variable, we put a double dot. Third derivative means triple dot. I think this notation is fine, I think, right? I don't think there is any confusion. Now, what kind of differential equation is this? I would say this is third order ordinary differential equation, third order linear ordinary differential equation. It's a third order linear ordinary differential equation, and the solution that we are going to get, you are going to get a value of y, right? The solution, so this is going to be the solution, right? If you solve this differential equation, again this is your input, xt is your input. If you solve this differential equation, you are going to get a value of xt as a function of time, right? And this xt will be a real number, real value, or maybe for our purpose this is going to be a complex number. Okay, for the most part, but say we are dealing with real signals and real signals, for example. Okay, so if we say we are dealing with real signals, then the result will be a real value here. It could be a complex value. Let me just say a complex value. Okay, so essentially I would get a solution in terms of yt if I just solve the differential equation, instead of going through all the issues of differential all the problems of transfer function. If we just solve this differential equation directly, we would get a solution here. Okay, for our convenience, let me just say okay, let's just say we are assuming real solutions. Just say for the moment we're assuming real solutions, because that would be easier for us to assume and understand. Okay, I think there is no issue with this, right? Okay, now Kalman thought, now this is a very difficult system, right, really, to deal with. What is the easiest, what is the simplest, rather, what is the simplest question is, what is the simplest system, really? What is the simplest system? Now my question is not that clear, I think. What is the simplest dynamical system, right? What is the simplest form of a dynamical system? The simplest form of a dynamical system, or dynamics, again this is a dynamic system, would be a first order system, right? The simplest, so this one is the easiest one. Okay, if I give you a system that actually has a differential equation that looks like this, y dot equal to say y dot plus a1 y dot plus a0 y equal to b0x. See, this is the first order ordinary differential equation, but this is the simplest first order ordinary differential equation. Okay, this is really the simplest first order ordinary differential equation, and first order linear ordinary differential equation, simplest one, right? You can see something like that. So Kalman thought, okay, and we can solve it very easily, right? We also know the solution. We can solve it very easily, right? The problem is the Kalman tried to think about a way in which he could convert this entire differential equation, this thing. He wanted to convert this entire big, huge differential equation into a differential equation that looks like a first order ordinary differential equation. Try to understand the objective here. Kalman wanted to convert this differential equation that looks like this to just a first order ordinary differential equation. And fortunately enough, he had a bit of knowledge on differential equations. Okay, this is a book on differential equation. Okay, this has got nothing to do with control system engineering, but you would see that there is a chapter on state space modeling on this in this book. Okay, so you can understand that Kalman had a lot of knowledge. Kalman had a lot of knowledge on mathematics mostly. Okay, and so he then figured out using his mathematical skills that yes, indeed there is a technique that can be used to convert this nth order differential equation. This is essentially an nth order differential equation. You could take as many derivatives here as well. Okay, and convert this nth order ordinary differential equation into a single first order differential equation, into a first order ordinary differential equation. How would he achieve that? So he did actually achieve that. Try to just let that sink in. I am converting a third order differential equation into a first order differential equation. I am going to do that because the moment I can convert this to a first order differential equation, we have a very simple solution, right? We have a very simple and easy solution for this, right? Really. Okay. So he wanted to convert this entire thing to a first order differential equation. Okay. So that is what he did. So he tried to follow this and he tried to figure out a way in which he would be able to convert this into a first order differential equation. So let me write down the equation once again. Okay, and then he figured out, okay, what if instead of writing this as third order differential equation, okay, it's a third order differential equation, instead of writing this as a third order differential equation, what if I can split this differential equation into 3 first order differential equations, right? So the objective is now to reduce this, or rather split this into 3 first order linear ODEs. Now this was a single third order ODE, okay, third order ordinary differential equation. Now objective is right now to split this into 3 first order ordinary differential equations, okay. And indeed this is, and when you ask a computer program to give you the solutions of transfer function models and everything, under the hood this is the modeling they do, okay. This is very computer friendly, I would say, okay. And you would see why, because in order for a computer to actually do proper computations, the process should be pretty systematic, right? It should not be ad hoc. But the transfer function modeling is pretty ad hoc. Depends on if you have this, then do this, then think about it, then do this. That is how transfer function modeling really works. But in state space, everything is so systematic that you have proper algorithms, proper ways in which you can proper ways that you can follow blindly, and you would end up with the correct result. Okay, this is how these things are designed. Okay, so now the very first thing that you have to understand is that in this model we are going to assume a few things, and the assumption is not going to be some rather we're going to consider a few variables rather. Okay, we are not going to impose any conditions, right? Sometimes when we assume things, we impose new conditions on things. We are not going to impose any condition. Okay, we already imposed linearity and time invariance. Okay, and apart from that, we are not going to impose any condition right now. Okay, just to remind you, we imposed linearity and time invariance because your course is on linear systems. Okay, I cannot impose non-linearity here. Okay, that is why we are studying linear systems. Otherwise we would actually see how we model non-linear systems as well. So now we want 3 first order differential equations out of this 1 third order differential equation, right? So we are going to now assume 3 variables here. Okay, we are going to assume 3 variables, and okay, let us assume 3 variables. Now what are the variables? We are going to assume 3 variables. We are going to call them x1, x2 and x3. Okay, so when I say I want 3 differential equations, I would want 3 differential equations that are not related directly with each other. Okay, we will see what I mean. Okay, now this is the third order differential equation, right? I am going to assume something like this. Okay, I am going to assume, now this might look like an ad hoc assumption, but it will be pretty clear shortly. I am going to assume this to be y, this to be the first derivative of y, this to be the second derivative of y. Okay, let's see what these assumptions actually result to. Okay, I just assume 3 variables. I just brought 3 variables to existence here: x1, x2 and x3. And x1 is just, I have defined this as y, x2 I have defined this as y dot, and x3 I have defined this as y double dot. Now see, it is not like we are assuming something that wasn't there earlier, right? We're assuming something that was there already, right? Y is already there, y dot is already there, y double dot is already there in this differential equation. We are assuming things that are already there in this differential equation, that are not some sort of an ad hoc. This is not some sort of an ad hoc assumption, right? I think that's fine, right? So now if this is x1, if x1 is y, then I can also say x2 is y dot, which is going to be x1 dot, right? And if I have assumed that x3 is y double dot, then then this is x2 dot. See, and this is also, since this is x2 dot, this is x1 double dot. See if that is fine. Okay, x2 is already x1 dot. Okay, so x2 is already y dot, so x2 dot would be y double dot, and x1 double dot of course is y double dot, the same thing. Okay, so that is kind of correct, right? That is correct, no issues, right? Now let's take this differential equation. Okay, let's take this differential equation. So therefore this differential equation, so this is, say, equation number 1. I would say 1 becomes, so if I take this differential equation, and we have, I think you can see this, right? We have a3 y triple dot. So how would I write a3 y triple dot? A3, what is y triple dot? Can I write this as x3 dot? Okay, then we have a2 y double dot. So a2 y double dot, but what is y double dot? That's x3. Okay, then we have a1 y dot. Okay, so what is y dot? Y dot is x2. Okay, then we have a0 y. A0, what is y? Y is x1, and the input is x. Okay, the input is x. Okay, rather let's do one thing. Instead of calling the input to be x, from the beginning let's call the input to be u. That's gonna reduce a bit of confusion here. Okay, again, u is just a name here. U is just a name, so don't worry about that. U is just going to be a name here. Okay, u is not corresponding to step input or anything of that sort. It is just a name. Okay, I'm considering u to be the input. Again, it is not the step input, it could be any input. Okay, all right. And that should be equal to b0 u for this purpose. Okay, now look at this differential equation. If I just look at it very simply, we will see that, okay, it's a differential equation that is, what is the order of this differential equation? Really, if I give you a differential equation that looks like this, what is the order of this differential equation? Truly speaking, this is the first order differential equation. Look what we have done. So this kind of looks like a first order differential equation. So let's simplify this a bit. Okay, let's simplify this a bit. So I am writing a3x dot, and that's going to be equal to minus a0 x1 minus a1 x2 minus a2 x3 plus b0 u. Okay, and then I can write x dot is equal to minus a0 by a3 x1 minus a1 by a3. So now you can understand why I wanted to divide it earlier, right? I will have to divide it anyway. So that is where a3 actually goes. Okay, on the denominator of everything, x2 minus a2 by a3 x3 plus b0 by a3 u, right? Now sorry, that's x3 dot, right? So now notice very carefully, we have a differential equation. This is just a differential equation. Okay, this one is a differential equation, but this differential equation is, what is the order of this differential equation? If you know nothing about x1 x2 x3, if you have never seen them before, okay, what is the order of this differential equation? This is the first order differential equation, right? Look very carefully, this is the first order differential equation, first order ordinary differential equation. All right, and how is that useful? Because Kalman wanted to convert this nth order system, any system, into a standardized, okay, he wanted to convert everything to a standardized first order system, so that the techniques he would develop to solve that system, to figure out the internal workings of that system, is applicable for every single system, right? So if we can convert every type of model in a single form, right, then once we can convert everything into a single form, then whatever techniques we develop for that particular form will be usable everywhere for every single system. Now this is not true for transfer function. For transfer function, if you have this kind of transfer function, then do this. If you have that kind of transfer function, then do this. Okay, there are so many things. Now Kalman's intention here was to convert everything into a single uniform form, okay, so that whatever technique he develops would be applicable for all different systems, all different kinds of systems, that can be converted into a single uniform form here. Okay, and this would be even easier for us to implement using a computer, because once we have a single uniform form, single uniform structure, we can, and standardized rules, okay, then we'll be able to implement those using algorithms and computer programs very easily, right? Because everything is so systematic, everything can be modeled pretty easily, right? Understandable, I think. Okay, so that's one differential equation. If you know nothing about it, nothing about x1 x2 x3 here, you would say that this is a first order differential equation, right? But again, the story is that it is a third order differential. It was originally a third order differential equation, but we turned this into a first order differential equation. But that cannot happen. We would end up with 3 first order differential equations, because that was our intention here. The intention here was to split this into 3 first order linear ordinary differential equations. Where are the rest 2? The rest 2 are actually here already. Okay, the other 2 are, so this is one, right? Let me just copy it. So let's keep that in mind. So I would say the differential equations, the first order differential equations, the 3 first order ODEs governing the system are, so this is one of them. So this is one of the differential equation that is governing the system. And what else do I have? I need to have 3 differential equations, obviously. Okay, 3 first order differential equations. So what else do I have? I already have the other 2 here. Notice very carefully, the other equations are x1 dot is equal to x2 and x2 dot is equal to x3. So x1 dot is equal to x2 and x2 dot is equal to x3. Okay, so I think this is fine and all. So what we have done, essentially, we have converted the third order differential equation, a single third order differential equation. This was a single third order differential equation, this thing. Okay, a single third order differential equation into three first order differential equations. Okay, now what is the point of this? The point of this is that we can write this in the form of a matrix. Okay, in the form of a matrix. So I can assume this to be 0x1 plus 1x2 plus 0x3 plus 0u. Okay, 0x1 plus 0x2 plus 1x3 plus 0u, something like that. I can make an assumption that looks like this, and now I can write this down in the form of a matrix. So these three equations can be written in the form of a matrix like that. So this is going to be x1 dot, x2 dot, x3 dot, okay, and this is equal to, notice very carefully, I believe all of you understand how matrix multiplications work. All right, so now here I am writing x1, x2 and x3. Okay, so let me get rid of my head here. All right, so all of you understand this, I think. All right, so now whatever element I have here gets multiplied with x1, whatever element I have here gets multiplied with x2, whatever element I have here gets multiplied by x3, and whatever I have gets added, and that becomes x1 dot, right? We know that. So if I write the equation for x1 dot, that is 0 1 0, and here I have 0. See, 0u rather. Okay, so this becomes, after the multiplication, 0x1. Okay, so after the multiplication this becomes 0x1, okay, plus 1x2 plus 0x3 plus 0u, and that is equal to x1 dot. Okay, so we already know that, right? What about the next one? In the next one I have 0x1 plus 0x2. So in the next one I have 0x1 plus 0x2 plus 1x3 plus 0u. So 0 multiplied with x1, 0 multiplied with x2, 1 x3, okay, so and 0 u. Okay, and for the last one, so this is again, if you do the multiplication, so 0 x1, 0 x2, 1 x3 plus u, that is giving you x2 dot. All right, and for the last one I have minus a0 by a3 minus a1 by a3 minus a2 by a3. Okay, so essentially what happens is, and here we have b0 by a3 u, right? Of course, this is the reason why I wanted to divide everything by a3 in the very beginning. So I would have minus a0 minus a1 minus a2, just like that. Okay, so of course this actually means that this is x3 dot equal to minus a0 by a3 times x1 minus a1 by a3 times x2 minus a2 by a3 times x3 plus b0 by a3 times u, right? So I can bring my head back now. So I think you understand the objective here, right? And here, of course, instead of writing u after everything, hold on for a second. Instead of writing u after everything, I can get rid of the u, or rather take u common out of this. Okay, factor out u and write it outside. So that's gonna be. So now this is a matrix. This is a matrix, or rather a vector. Okay, what is the order of this vector or the matrix? This has 3 rows and 1 column, right? This has 3 rows and 1 column. So this is a vector of 3 by 1 vector, right? Okay, this matrix, this is a 3 by 3 matrix. This is again a 3 by 1. This is again a 3 by 1. This u is a scalar quantity, so it is 1 by 1. Okay, these are the dimensions, number of rows times number of columns, right? Now if I consider this matrix, if I consider this vector, okay, so say we write this vector, this one. Say we write this as x. Again, all these x, they are functions of time. Okay, all these x and y, all these things are functions of time. That is understandable. So now this x is a matrix. So a matrix is written really, so if I symbolically present a matrix, so that would be represented in a bold letter in a printed format. Okay, or if I type it in a computer, I would write this in bold letters. Since I am writing it by hand, I would put underline on it. Okay, this represents a matrix. Okay, so this is underline or bold letter, so just keep that in mind. This would be bold letter in print or underline in handwriting. So you'd have to either put a bold letter or underline it while you are writing it by hand. Okay, so just keep that in mind. Okay, so this is a matrix, right? Just keep that in mind. Okay, and what about the next one? Then if this is so, then what about this? What about this? Then what happens with this? Then what is this derivative? This is essentially the derivative, the first order derivative on top of, okay, x1, x2, x3, this vector. This is the first order derivative on top of this. So essentially this is the, again, first order time derivative on this vector x. Okay, this vector x. Okay, and that can be simply written as x vector and a dot. So this is now a vector. Okay, x vector is the vector of x1, x2 and x3. Okay, so the derivative of that vector is this. Okay, now let's assume this is a matrix, right? This is a matrix. Now assume this is a matrix, right? Let us assume this to be another matrix and give it a name. That's A. All right, that's A. Let's call this A. Okay, let's give it names. Okay, and here we have another matrix. Again, I am just showing you a very special case, special example here, and let's call this matrix B. Okay, so if we give it these names, then what happens to this equation? So this is my equation number 2, say. Okay, This is my equation number 2, which is in the matrix form. Okay. Then equation 2 becomes, what happens to the equation 2? See, this is, what is this? What is this part? This derivative part. That is x dot in the matrix form. What is this matrix? That's A. What is this matrix? This is X plus. What is this matrix? That's B and then U. So this equation 2 just becomes the derivative of this vector equal to A matrix times that vector plus B matrix times the input. And now input is a scalar quantity here. The U is a scalar quantity because I had only a single input in the system. If there are multiple inputs, U will also be a matrix here. Now here in this particular case, U is a scalar quantity. But if I have multiple inputs, U would be a vector quantity. Okay, it will also be a vector. Okay, now see, what differential equation is this? Isn't it very similar to a differential equation that looks like this? X dot equal to ax plus bu. Okay, just a simple first order ordinary differential equation, right? So this is now a first order ODE in R3, I would say. Okay, but now instead of x, previously, look very carefully, previously the solution was just a real number at any given point. Okay, now here the solution, when I solve this differential equation, I would get x, right? And what is x? X is really x1, x2, x3. So I would get 3 points here, 3 solutions, right? 3 things, right? So in this I would have 3 values, right? And that is basically a member of R3. R3 means 3 real numbers, right? All right. I'm going to talk about diagonalization, whatever, later on. Okay. So that, keep that in mind. So what we have done really, we have converted a whole system here into a first order differential equation, and this is the standard form. The moment you can convert something to a standard form, you understand that whatever techniques we develop for one of them will be applicable for all of them. This is the idea here. Okay. So the moment we can convert any system to a standard form, okay, whatever technique we develop for one of them, that technique will be applicable for all of them with any minor modifications, if at all. Okay, so that is the idea here. All right, and there is just one small point here to also note, is that with this we also need to figure out the output. We haven't yet talked about the output. What is the output of the system? What is the output of the system? In this entire story, we just completely forgot about the output, right? We are assuming y here, u is the input and y is the output. But this is just an assumption. Once again, we can consider anything to be the output. Okay, we can consider y dot to be the output, y double dot to be the output, or whatever, right? Now if y is the output, then what happens to y? What is y really? Y is, notice very carefully, y is x1, right? Output is x1 here, right? So if we consider the output here, so y is the output. I'm having stream related issues, I think. Please let me know in the live chat whether the stream is fine or whether it is buffering for some of you. Because something is going wrong with the stream, I think. Please tell me whether it is buffering for you or if it's fine. All right, thank you for confirming. All right, so what is y here? Y is x1, but I cannot write x1 anymore, right? So what is x1? X1 is nothing but 1x1 plus 0x2 plus 0x3 plus 0u, right? So here, really speaking, on top of this, I would also need to write, along with this, I would also need to write the other equation. What is the output? Let us write this with different thing. The output would be, okay, 1x1 plus 0x2 plus 0x3, okay, plus 0u, something like that. So if I really write that in the matrix form, this would be y, which is equal to 1 0 0, and then I would have x1 x2 x3 plus 0 u, really. Okay, now again, just like the previous one, we would assume this, I assume this, okay, this is here, this is a 1 by 1. Now this is a scalar quantity because 1 by 1 is a scalar quantity. This is because the system we have assumed is a single output, single input, single output system, single output. That is why we have a scalar quantity in the output. So this is a 1 by 3 matrix, so 1 row 3 columns. This is again 3 by 1. This is just like the previous one. This is 1 by 1. Okay, this 0 is a scalar quantity, and this u is also a 1 by 1. Okay, so we are assuming this matrix, this one, 1 0 0, whatever we have here, to be another matrix. We are calling this C. Okay, and this 0 here, we are calling this the matrix D. Okay, so this one, okay, let me just write it here, otherwise writing this here won't be useful. Okay, matrix D. Okay, so this equation can now be rewritten as y equal to C x, see these are two matrices, plus D. Fortunately here D is a scalar quantity because of a single input single out, because we have a single input single output system. And don't worry, we would deal with multiple input multiple output systems later on. So we have two equations. See, this is an algebraic equation. This equation is an algebraic equation. This is not a differential equation. This is an algebraic equation, right? And this one is the first order ordinary differential equation. So if I just write them together, okay, so we had a single system, we had a single we had a very simple system. So we had a third order system. Okay, again, it doesn't have to be third order, it could be of any order. Okay, and we converted it to one differential equation, one. So we convert this to one differential equation and one algebraic equation. See, we did not make any assumption during this, right? We did not make any assumptions that wasn't there before. Now this is the standard form, and the thing is, if I give you any linear time invariant system, you would always be able to convert the mathematical model into this standard form. Any given linear time invariant system can be converted into this standard form. Okay, and only based on the order and based on what parameters you have, only the values of matrix A, matrix B, matrix C and matrix D, these will change. Okay, A, B, C, D, these matrices, the values will change. Only these values will change, nothing else will happen. Okay, so whatever mathematical technique, whatever control system technique, control design technique, control analysis technique, system analysis technique we develop will be applicable for all of them. The technique we develop for one of them will be applicable for all of them. The technique we develop for this configuration will be applicable for any system that can be written in this configuration. That is the point here. Okay, that is the sole point here. Now here are a few names that you have to keep in mind. Again, the names will be pretty clear as we proceed with the discussion here. This x here, okay, is known as the state vector. This is known as the state vector. Okay, this x dot is the derivative of the state vector. This matrix A is the system matrix. This matrix A is the input matrix. Okay. Matrix C is the output matrix. And matrix D is the feed forward, also known as measurement matrix. In this one, this is not a matrix, this is a scalar quantity, but I am going to call it a matrix anyway. Okay, so these are the names here. Okay, and this equation itself here is known as the state equation, and this equation is known as the output equation. Now with this construct, we actually can have better insights about our system. See, under these, while doing this, we never assumed the condition of zero initial conditions, right? We never assumed that the system will have to have single input, single output. We assumed linearity because the differential equation itself was a linear differential equation. So this differential equation itself is a linear differential equation. So we assume linearity with these conditions because your course is on linear control. So I cannot assume non-linearity because of that. Otherwise we could have. And these are the equations in which, using which you can represent the system. Okay. So now the understanding is that whatever methodology we develop will be applicable to all the systems, really. So this is going to be a very systematic approach. Now about the names here. Okay, this x here is the state vector. Okay, this is essentially carrying all the output variables. So y dot, y double dot, all these output variable and their derivatives are being carried by this x here. Okay, so this is called the state vector, and we shall see with proper examples how that actually translates to real life situations. Okay, this u is the input. Okay, and x dot is the derivative of the state vector. So this is essentially everything to do with the states, right? So this is the state vector, derivative of the state vector, and how the system really behaves. Okay, so this is why this is called the state equation. Now of course this matrix A is called the system matrix because many of the behaviors of the system, including stability, including the Bibo stability of the system, is only dependent, or rather entirely dependent, on the matrix A. And soon we shall use certain techniques of linear algebra to figure out what this matrix A actually means. Okay, what is the significance of that matrix A? But let me tell you, this matrix A is pretty much as important as the characteristic polynomial of systems. Okay, if you think about if you think about transfer functions, this matrix A is as important as the characteristic polynomial of the systems. Okay, you will see that soon enough. Okay, and matrix B is called the input matrix because this directly gets multiplied with the input. Okay, this directly gets multiplied with the input, and that somehow affects the resultant system here. Okay, so that is why matrix B is called the input matrix. Very similarly, Y is the output. Okay, and matrix C somehow generates the output from the states. Okay, so this is the state matrix, and by multiplying the state matrix with this, with this matrix C you generate the output. That is why matrix C is known as the output matrix. And in the absence of this output matrix, or in the if you forget about this, then matrix D denotes the part of the input that directly gets fed to the input output, the part of the input that directly gets fed to the output. So matrix D is often called the feed forward matrix, or also known as the measurement matrix, the part of U that actually reaches Y directly. So this is again a standard model here. Okay, now let's solve a simple example and see how we can actually really deal with these things. Okay, let's see an example, proper real example. Let's see. Okay, okay, so another example, let's say an actual example. Okay, so let's take this, let's bring this out here. Okay, let's take this differential equation, and let's say instead of writing all these, let's put values here. Let's instead of put values here, I can do that, right? That'd be an actual example. So if I put values here, say for example 5, say I say 3, 1, 6, and say this is 10. Okay, let's say this is 7. So what would be the transfer function? You know that the transfer function is going to be GS is 7 by 5s cube plus 3s square plus s plus 6, right? That's going to be the transfer function, but we are going to keep that aside, because the moment we say transfer function, we are already opening a can of worms. Really, we are assuming quite a few things already under the hood. So that's going to be the transfer function, right? And again, if I give you a transfer function, you can always construct this differential equation easily, right? So if I have this differential equation, then what are we going to do? We are not going to write it once more, but instead we are going to simplify this very quickly. Okay, so think about this. This is A3, this is A2, this is A1, this is A0, right? We can start from the very scratch, very beginning. Okay, start from the scratch, but instead we are going to just write it down that this is a differential. This is rather, let's just do this once. Okay, all right. So we are assuming x1 to be y1, x2 to be y1 dot, sorry, y dot, x3 to be y double dot. These are the states. Okay, and we are assuming u to be the input, y to be the output. Okay, all right. So with that assumption, then this differential equation essentially becomes this differential equation. Let me just copy it, otherwise you won't be able to see this. This differential equation essentially becomes, instead of y triple dot, I would write x3 dot. Instead of y double dot, I would write y dot. I would write x2. Sorry, y double dot, I would write x3. Instead of y dot, I would write x2. Instead of y, I would write x1. And we, alongside that, we can now simplify this very easily. Okay, we can now simplify this very easily. Okay, you can simplify this very easily and write down x3 dot to be equal to minus 1 by 5, sorry, minus 6 by 5 x1 minus 1 by 5 x2 minus 3 by 5 x3 plus 7 by 5 u. Okay, that is one of the equations, and the other two equations are x1 dot equal to x2 and x2 dot equal to x3, right? So the equations really are x1 dot equal to x2, okay, x2 dot equals to x3, and x3 dot equals this. Of course, the output is nothing but y equal to x1. I'm assuming that. So in the matrix form, this can be rewritten as this one. This equation in the matrix form can be rewritten as this matrix, 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 like that, and I would have just one equal to symbol here. Okay, and this entire thing will become a matrix. Okay, and instead of doing that, I would write 0 1 0 0 0 1. So this, this, and this, so that would be just x1, x2, x3 plus I would have 0 0 and 7 by 5 and u. Okay, and here I would have y equal to x1, which is 1 0 0 times x1 x2 x3, and we have 0 u. So let's just write that 0 u. You could have skipped that. So really speaking, this is the derivative of, let's just, so this is essentially the derivative of vector x. This is really the derivative of vector x. Okay, this is equal to, this is matrix A times x, this entire thing, matrix A times x, and this is plus, this is b times u. Okay, and here this is y, this is y, this is equal to matrix C times x plus d times u. Here d is a scalar quantity. Okay, so these are the things you have. Okay, so you can represent any system in this form, right? I think it is not very difficult to see, right? So let's do a second order system. Okay, let's take another example. Let's say the transfer function of the system is, say, omega n square divided by s square plus 2 zeta omega n s, where zeta omega n are constants, and omega n square, something like that. Then what is transfer function? Transfer function is essentially the ratio of the Laplace transform of the output with that of the input. Now we are writing input to be us for our sake. That's going to be omega n square divided by, so it's a second order system, right? All right, so this is going to be s square ys plus 2 zeta omega n s ys plus omega n square ys, and that equals omega n square us All right. So now taking inverse Laplace transforms. Again, the moment we say we have a transfer function, we are assuming zero initial conditions. We are assuming linearity and time invariance. Now taking inverse Laplace transform. So this becomes y double dot, okay, of course a function of time, I'm not writing that, okay, plus 2 zeta omega n, those are constants, and this becomes y dot because sys, the inverse Laplace transform of that is y dot under zero initial conditions, of course. And then we have omega n square y, and that is equal to omega n square u, again it becomes ut, of course, no issues. Now we have to assume the state variables, okay. So assume the state variables. Now assume the how many state variables do I need? How many state variables do I need? It is equal to the order of the system. Obviously, see, when we converted the third order differential equation, we converted it into three first order differential equations by using the state variables, right? So these variables x1, x2, and x3 are known as the state variables, right? So and this are called the state vectors. So x1, x2, x3, these individually are called the state variables. Okay, so how many state variables do I need? Okay, since it's a second order system, I need two state variables, and that would be equal to the order of the system. So I would assume x1 and x2, and just like the previous one, x1 would be y, x2 would be y dot. That's the end of it. These are the state variables. Okay, or that's simply called states, just called states also, right? You can just call them states. Okay, all right. And u is the input, u is the input, and y is the output. All right, so with that said, now if I write this equation with this, if I rewrite this equation, I said, then if I rewrite this equation, what happens to y double dot? What is y double dot? That's just x2 dot, right? What is y dot? Y dot is x2. What is y? Y is x1. Okay, and what is u? U is u, fine, no problem. Then what is x2 dot? X2 dot is minus omega n square x1 minus 2 zeta omega n x2 plus omega n square u, right? So that is one of the differential equations. Let's copy this. Okay, that's one of the differential equations. And what is the other one? Other one is, of course, that x1 dot. And what is that x1 dot? X1 dot is essentially, we already know that x1 dot is nothing but x1 dot is nothing but x2, right? Because let me just assume it wrong. So y dot is nothing but x1 dot, right? Because y is x1. So other equation would be simply x1 dot will be equal to x2. So that's just x2. Okay, and what is the other equation? The output equation represents y, which is equal to just x1. Okay, so now in the matrix form, I can pretty easily write these in the matrix form, right? I can. So that's, we have here, we have a matrix representing the state derivative of the state vector, so x1 dot and x2 dot, and that equals 0, 1 minus omega n square minus 2 zeta omega n x1 x2 plus, I know my head is blocking it, 0 omega n square u. So these are the first two equations, of course. So this is the state equation, and then we have y equal to, that's just x1, so there's going to be 1 0 0, sorry, 1 0, just 1 0, x1 x2 plus 0 u. You can write this, you can skip it if you want. Okay, so here once again this is the derivative of the, so this is the state vector. Here once again this is the state vector. Okay, this is the state vector. Okay, and this is the derivative of the state vector once again. All right, and this is equal to, this is matrix A, this entire thing is matrix A. Okay, so we have matrix A times the state vector plus, this is matrix B once again, this is matrix B, so matrix B times U. Okay, again U is a scalar quantity because it's a single input. And here we have matrix Y, or it's a scalar quantity here in this one because it's a single output system. And this matrix is, this is matrix C, so C times X, again state vector, plus here this is a scalar quantity D times U. See, the idea is that we can represent all of our systems in this standard form. That is the idea here. Okay, if I give you any system, you can convert this to this standard form, right? Standard form. So now I have already talked about first order system, second order system. Let's do a third order system. We have already talked about second order system and third order system. Let's do a fourth order system, shall we? Okay, so let me give you a transfer function, very easy transfer function once again, and I shall ask you to, so whose transfer function looks like this. Right, so construct a state space model out of this. You can understand what the orders are going to be, right? Try to figure those out. Okay, and notice the wording here. I am saying a state space model, and I'm going to clarify what I mean by a state space model. I'm not saying the state space model here. Okay, I'm not saying the state space model, I'm saying a state space model. Okay, there is a reason for that, very important reason for that, which we will establish later on. But again, just try to do that. I'll give you like 2-3 minutes. If you can, then you'll be able to do this within 2-3 minutes, I think. All right, so I think many of you have tried. So the answer, right? So with this, what we are going to do, we are going to again write this as ys by xs, and that's going to be equal to this thing. Okay, and then of course we are going to write ys equal to ys times this, the denominator, and then xs times this, and then we are going to apply inverse Laplace transform. So eventually we are going to end up with y quadruple dot. So instead of writing quadruple dot, I write 4. Okay, y4 plus, let's say put quadruple dot, no problem. Okay, plus 7y triple dot plus 3y double dot plus 9y dot plus 10 y equal to 10x. Okay, how many state variables do I need? Now I need 4 state variables because it's a fourth order ordinary differential equation. I want it to I want to convert this into 4 first order ordinary differential equations. So I need state variables. So declare state variables. So my state variables are x1, x2, x3, x4. Again, the way we are assuming the state variables is a special kind of state variables. Okay, this is, we are assuming the state variables in a special way. There are infinitely many different ways in which you can assume your state variables, and since there are infinitely many different ways in which you can assume your state variables, there are infinitely many state variable representations of a same transfer function model. So if I give you a system, so this is kind of one disadvantage if you think about it. If I give you a system, for that unique system you would probably have one single transfer function, but for that system you can have infinitely many different state space representations. You understand my point? If I give you a single unique system that has one transfer function, that can have infinitely many different state space representation. So this apparently might seem like a disadvantage, but the advantage is that we can use the that state space model which is useful for our purpose. So the way we are doing state space modeling right now is useful for the purpose of modeling. So if I want to model my system in the state space, this is the way in which we model systems. But if I want to design a controller for our system, then we might want to convert the system into a different form depending on the way I need it. Okay, if I want to design an observer for a system, and what is an observer we shall learn later on, then we shall convert the state space model into another suitable state space model in which designing an observer becomes easier. The point being, since we have infinitely many different representations in the state space for the same system, we can at our will convert the state space model into another state space model that is equivalent and that is suitable for designing a controller, maybe designing an observer, maybe doing some other things with it. Okay, but nevertheless the system representation will always look like this: x dot equal to ax plus bu and y equal to cx plus du. The representation will always look the same. Okay, but the exact values of x, y, a, b, c, d, these matrices will be different based on our assumptions. Okay, how we defined our, or rather declared our state variables. Now here the declaration we are doing for our state variables is that we're writing x1 to be y, x2 to be y dot, x3 to be y double dot, and x4 to be y triple dot. Here as usual, since we have a fourth order system, we are assuming 4 state variables. So this is fine. This is x dot, x1 dot. This is going to be x2 dot, which is x1 double dot, and this is going to be x3 dot, which is x2 double dot, which is x1 triple dot, and of course my u is the input and y is the output. All right, so with that assumption, let me just copy the differential equation here. Okay, and instead of y quadruple dot, I would just write x4 dot. Yep, someone has already got part of the answer. you cannot you cannot write a matrix here. Okay, but just try to follow along. If you have done it correctly, you'll find. So here we had y triple dot. Y triple dot would be just x4, and y double dot would be x3, y dot would be x2, y would be x1. Oh, did I just write x? Oh, this is again the way I've been doing this forever, literally. This is u. Actually, u is the input. Okay. All right. So that's it, right? So that is the differential equation after the conversion. This is what becomes of it, right? After this assumption. So this way, if we convert this and figure out x4 dot becomes minus 10x1 minus 9x2 minus 3x3 plus 10u. Okay, so now we have to write this in conjunction with the other 4. So we have to write this in conjunction with the other 4. All right, so the other 4 are thus. Shabash, one of you have done it correctly. Okay, so x1 dot, what is x1 dot? That's x2. Sorry, I had x4. Where is x4? I just completely skipped x4. Wow. Plus 7 x4, and that will be plus 10u. Sorry, minus 7 x4. Minus 7 x4 plus 10u. And I think I have to move everything to the left. All right. So x1 dot is equal to x2. x2 dot is equal to x3. x3 dot is equal to x4. See, these three are coming from the assumptions, and this is actually coming from the differential equation itself. Okay, these are actually coming from the assumptions, and this is coming from the differential equation itself. And of course the y output is just x1, at least for our assumption, as per our assumption goes. So these 4 represent the state equations, and this is the output equation. All right, and out of these 3 are actually coming from the assumptions, and the last one actually coming from the differential equation itself. So I think that is understandable, right? So now with this I can convert this into the state variable form proper. Okay, so then therefore we can write this as x1 dot x1 dot x2 dot x3 dot x4 dot c, and then we can write this as not enough space. So again, you are learning to represent different systems in the same way. So that is the point here. If we can represent everything the same way, then we can develop one technique that will be applicable for everything. Okay, we don't have to develop different techniques for different things and keeping on developing. Okay, so here, so this is like x1 dot, so x1 dot is equal to x2, so that's going to be 0 1 0 0. x2 dot is equal to x3, so that's going to be 0 0 1 0. x3 dot is equal to x4, so this is 0 0 0 1, and x4 dot is minus 10x1 minus 9x2 minus 3x3 minus 7x4, and again this is 0, this is 0, this is 0, and this is 10. Okay, and y is equal to 1 0 0 0, and this multiplication here. So x1, x2, x3, x4 plus here we have 0. You could skip that, could write this, keep it. Okay, but keep in mind that this is once again in the form that this is x, so this is a, so this is in the form once again ax, so x is this one is x, and this one is a, plus this is again bu, so this matrix is b. Okay, and this is once again the derivative of the state vector, so x dot. Okay, and here this is the output matrix, so this is the output, and this is again in the form of c x. Okay, this is c and this is x plus d. So this is the state equation and this is the output equation. But now I try to see that it is still in the same form here. Okay, just notice that. Got it? Yes, you have done it correctly. Nice. All right. So you have so far learned how to represent a differential equation, a system that is given in terms of a differential equation, into a state variable form, or if it's given as a transfer function, how to convert that to the state variable form, to a state variable form, equivalent state variable form. So here are a few points to note. Points to note. Okay. So number one, the number of state variables is always equal to the order of the system. Number two, now this is not a point to note really, but point to remember rather. Okay, points to remember rather. So you did not really notice this, but you have to remember this. We shall later on. Or someone is saying underline this. Can we write this as uppercase X? No, really, we are writing uppercase A to represent a matrix. Okay, but for vectors we use lowercase quantities, because A is a so this is the uppercase lowercase thing in engineering. The moment we write uppercase letters, it means it's a constant. Be it a matrix, be it a vector, be it a scalar quantity. If we write uppercase letters, it means it's a constant. Okay, it's not a variable quantity. Okay, but if it varies, then we use small letters. Okay, so we are writing capital A to represent the system matrix because it's a constant. Look very carefully. It's a constant as far as we are as long as we are concerned. For this particular system, A is a constant. It's a matrix, but it's a constant. So that is why we are using capital letter here. But this state vector is a variable quantity, right? It changes with time. It changes with time. So since this changes with time, I have to use a small letter to represent that. And since it's a matrix or a vector, I'm writing underline. Okay, just like that. So this is a kind of an engineering notion here. Okay, so variable quantity represented with small letters, constant quantities represented with capital letters, uppercase letters. All right, so good question. So points to remember, I would rather say. Okay, a unique system, so basically the same system, has infinitely many equivalent state space representations. Point is, this is not a disadvantage. This is actually an advantage. And notice the point equivalent. Okay, so I can represent it in many different ways. Okay, the way we have done it today has a special name. Okay, the way we have done state space modeling. So mathematical modeling done using state variables is known as state space modeling, of course. Okay. The way we have done it today, the way we have done state space modeling today is known as the phase variable canonical form. Because the stream is buffering intermittently, I don't know what is happening. Let me just refresh it. I think it's working, right? So there are many other different forms, and even the phase variable canonical form that we are using has different ways of being dealt with. Okay, you can deal it with different in different ways. And the last important point, most important point here to note is that, or rather, point number 4, the most important point to note here is that a system that can be modeled using transfer functions can also be modeled using the state space, right? Modeled in state space. A system that can be modeled using transfer function can also be modeled in state space, but it is not necessarily the other way around, right? Because the moment you are modeling something in transfer functions, in the transfer function domain, you understand that you are assuming too many conditions on it, right? Linearity, time invariance, zero initial conditions and all, right? But for state space, those conditions are not there. But if I have those conditions, then also the state space modeling works. So if a system has a transfer function representation, then the system will definitely have a state space representation. But it is not true the other way around always. Okay, so if a system has a transfer function representation, a transfer function model, then it is definitely going to have a state space model, rather have state space models, I would say. Not a, writing a state space model is a bad thing. Okay, going to have state space models, but the converse is not necessarily true. So if I have a state space model, it doesn't necessarily mean that I would have a transfer function model. But for our purpose, since we are assuming that the systems are linear and time invariant, so having the thing is reversible for our purpose. But for but for us, since we are assuming LTI systems only, LTI systems, um, LTI systems, having a state space model ensures that we also have a transfer function model. because in our state space model we are assuming non-zero initial conditions. Then we have to just put zero initial conditions and we can get the transfer function model. Okay, because we are already assuming linear time invariant system, right? You know, get a transfer function. Okay, so these are the points that you have to remember in this particular one. All right, so with that said, I am going to end the discussion with a little bit of programming. Let's see, let's bring out Python. And just for the moment, let me just give you another exercise, just an exercise for you to solve. Okay, transfer function model to a state space model. So this is the transfer function model. Try to convert this to a state space. Right. So try doing this. Right. This is your homework. Okay? This is in no way the assignment, but this is your homework. Okay. Let's do a little bit of programming now. Yes, someone is asking, can we convert something from state space to transfer functions? Yes, of course we can, right? That is something we have written, and we are going to see that. We are going to see that in the next class. Okay, we are going to see a generalized way of doing that. Okay, of course we are going to see that. So let me switch to the screen here. Okay, let me just make it bigger. So I would import control as CT. Okay, so we have imported control module. See, I'm doing it in Spider because I want to do it in my local computer here. Okay, so if we have a transfer function model, we can very easily convert this to a state space model pretty easily. Okay, so say G is equal to a transfer function model, whatever. Say G equal to, so first of all, S equal to ct dot tf. So this is the way I like to do it. So G is a transfer function model. So by now I believe you know how to write down transfer functions, right? So so ct 1 divided by, since I have defined s, I can just do it any way I want. So let's take an example that we have already done. Let's take the last one here. So that's gonna be 1 7 3 9 10. Okay, 10 divided by 1 7 3 9 10. Okay, you know what, doing this in this way would be better. So 10 divided by 1 7 3 9 10. This is going to be a better way, right? Writing all those powers will be a difficult one. So 1 7 3 9 10. Okay, right. So that's G. If I print out G, okay, this is 10 divided by s to the power 4 plus 7s cube plus 3s square plus 9s plus 10. I believe you can see this. All right, so that's fine, hopefully. Okay, so now if I want to convert this into a state space models, all I have to do, I have to call the state space model on it. Okay, rather, so I have to call this function transfer function to state space and pass in a transfer function. See, I passed in transfer function to state space this, and this gave me the state space model. But here, look very carefully, the way they have implemented the state space model is slightly different from ours. Okay, is slightly different from ours. In our model, we ended up with -10, -9, -3, -7, and this is what their matrix look like. Okay, so they have a different representation, and I can tell you what representation, how they have got this representation. Okay, the way Python is doing here, okay, the way Python is doing here, they are just assuming the thing in the reverse order. Okay, they are just assuming the thing in the reverse order. So they are assuming this to be x4, so they are assuming x4 to be equal to y. No. Also, someone is saying the last row has been taken to the first one. No. There is also a reversal here. Okay, so the way Python is doing it here would be is actually assuming, it is assuming that x4 is equal to y. So for the Python module that we are assuming, so it is assuming x4 to be equal to y, x3 to be equal to x4 dot. Okay, so let me just write it down. So for your sake, you can verify this. Okay, extra note here, extra note. Okay, if I ask Python to convert this okay, let me just erase this. If I ask Python to convert this, and this, by this I mean this transfer function, this transfer function model, this to a state space model, then again I'm saying a state space model. Notice very carefully, state space model, it assumes the following states. It assumes the following states. So you have to assume 4 states, right? The way we did it was x1, x2, x3, x4, right? Like that. Now it is, they are going to assume x4, x3, x2, x1. Again, these assumptions are equivalent. Okay, and they are assuming x4 to be equal to y, x3 to be y dot, x2 to be y double dot, and x1 to be y triple dot. So they are just assuming it in the reverse order. Okay, so this is going to be x4 dot, this is going to be x3 dot, but also equal to x4 double dot, and this is going to be x2 dot, sorry, x2 dot, and which is going to be x3 double dot, which is going to be x4 triple dot. Okay, so this is the assumption they are making, and thus their output y is u is still the input, y is still the output. Now of course y is going to be x4, not x1. Y is going to be x4. Keep that in mind. So this is the assumption they are making. So if you make this kind of assumption, your answer will perfectly match up with this. Okay, just keep that in mind. Okay, just keep that in mind. So this is again one way of dealing with. So I wanted to show it to you because there are infinitely many possibilities. There are infinitely many possibilities while dealing with this modeling, this type of modeling techniques. Okay, but you should be able to stick to one of them only. Okay, and there is also one corresponding difference here. Instead of writing 10 here, okay, instead of writing 10 here, they're writing the 10 in the output matrix. We are going to see how these kind of transformations really work in the next one. Okay, we are going to see those as well. Okay, all right. So for now, if we assume the next one, if we assume this, okay, if you assume this, it will work this out this way out. And now someone is saying, how would I know that the model that we have done is correct? The model that we have done is correct. How would I know the state space model that I have done is correct? So you can always do the other way around. You can put the state space model in Python and ask it to give you the transfer function model, because there are infinitely many state space model. The way you would do the state space model would be different from the way I would do a state space modeling, but the transfer function would be always the same, right? So instead, let me just write down the transfer function, the variables that we actually got, that we actually got, right? So matrix A, what is matrix A? What is the matrix A I got? This was 0 1 0 0. So this is what I got: 0 1 0 0, and then 0 0, okay, and 0 0 0 0 0 1 0, and then you know how to write matrices, right? 0 0 0 1, and then I think all of you can see it, right? And then minus 10 minus 9 minus 3 minus 7, minus 10 minus 9 minus 3 minus 7. And again, it is going to do it numerically using employing certain numerical methods. I have A matrix inserted. Matrix B is going to be 0 0 0 10, but in the transpose form. So it's going to be 0 0 0, so a vertical one, right? 0 0 0 10. So the point is, I would ask it to give me the transfer function. So this is the state space model we developed, right? C is going to be 1 0 0 0. So that's going to be 1 0 0 0, and D is going to be 0, right? And let me ask it to give me the transfer function. Okay, so from the control system library, I would call the function state space to transfer function, and I will pass it the state space model. So essentially, what is the state space model? These matrices A, B, C, D, right? They define the state space model for a system, right? A, B, C, D. They are going to be different for different systems. Other than that, x1, x dot, x, u, y, these are the same thing for all of them, right? So in a sense, A, B, C, D, these are the only things needed to construct the state space model. So I will call this function ss2tf and pass in the state space model and ask it to calculate the transfer function. Only one gotcha is that it is going to apply certain numerical method to do that. So we might end up with certain round off errors, but don't worry about that. So this is the transfer function model they have given me. Now notice very carefully, we have certain round off errors. We have a power of, can you see this? We have a, look at the denominator. First of all, look at the denominator. Is the denominator perfectly matching with our expectation? I wanted the denominator to be what? What was our model? What was the denominator? Yes, it was s to the power 4 plus 7 s cube plus 3s square plus 9s plus 10. Exactly, the denominator is matching. Now, when you look at the numerator, look very carefully that in the numerator, you have these very small terms here, 10 to the power minus 15 s cube. So this term can be ignored. Then we have 10 to the power minus 15 s square. That term can also be ignored because these are very small terms. These are there for round off errors because of the numerical methods this system is applying here. And then we have 10 to the power minus 14s. Okay, that can be also ignored. The only term that has any significant value here, which is this 10 here. So essentially, if you just think about it, this transfer function is nothing but 10 divided by this denominator, because everything else here are because of round off errors in calculation. So those terms are there for the round off errors in calculations. Okay, they are just there because of that, essentially. Okay, so this is just 10 divided by s to the power 4 plus 7s cube plus 3s square plus 9s plus 10. So this is exactly the transfer function, because transfer function is unique. The state space model can differ based on how it. Okay, so do you want a screenshot of this? Okay, so let me just take a screenshot of this and attach this. So in order to verify our integrity here, I can right. So maybe write down that this is how you verify the correctness of your state space model. And here notice that these terms, these terms, these terms, these terms, they're so insignificant that this can be reduced. Are so small that they can be ignored. All right. So this is again, this is the way you actually convert this and figure this out, right? Again, this is the assumption they are making. Again, nonetheless, you assume the way we would do. I have taught you. Okay, you construct the state space model. You will see that you are ending up with the correct result. So this is going to be your homework. Any question that you might have? And we are going to see the power of this method soon enough. All right, so thank you very much, I think. And again, you have already seen that if you pass in that to the TF to SS function, transfer function, then if you pass in a transfer function to TF to SS function, it gives you the state space model in their form. These terms are right. All right, so thank you very much. And if you have some other issues with regarding something else, you can contact me later. All right, so thank you very much. I will see you next week. I think maybe we shall arrange one additional class maybe this week to clear up your doubts regarding the previous topics. But anyway, this is going to be the end of today's discussion. So thank you all for being here, being patiently following what we are discussing so far, what we have been discussing, because you are going to see the real power of this later on. You haven't yet seen the real power of this method. Okay, so again, this is the start of modern control engineering for you. Thank you very much. Okay, I will let you know about the next one.